Okie dokie. So, what sort of things do you remember about what we talked about last year for Lewis structures?
Just remember the bond.
You just remember the bonds and the dots. All right. So let's go through and actually make some of the molecules that I talked about to kind of understand what we were thinking about last year and then how is it going to extend this year. So the first one I had you guys make is the methane. So that's the carbon and the four hydrogens attached to it. That one there. Um, you can't obviously make that with this guy, unfortunately, because it doesn't have methane as an option, but that's all right. Next one was carbon dioxide. So again, we take the carbon, here's our oxygen, here's our other oxygen, that's carbon dioxide. Next one was water. Here we go, H2O. Screen a bit brighter for you. Where's that? There you go. And then the last one was ammonia, which is this guy here. All right. So what is something that you observe that is like a consistent pattern between all these four molecules?
Double.
Some of them have double bonds. So just be mindful that these two electrons here doesn't mean double bond. It means that there's a single bond because there's two electrons in each bond.
Okay.
Okay? What do you notice about the number that these various atoms are trying to reach when it comes to those electrons?
8.
8, yep. So carbon here, 1, 2, 3, 4, 5, 6, 7, 8. Oxygen gun, 8. Nitrogen, 8. Uh, the carbon and the two oxygens both 8 as well. And then hydrogen is an exception to the rule. It only needs 2 because it's a smaller atom.
Okay.
All right, so that's kind of what I wanted you guys to realize with that. I will refresh Lewis structures from last year to kind of understand why did this one make a double bond, but these guys didn't. With the Java lab, I was hoping for you guys just to kind of see what's happening with the behavior. So here's my hydrogen, here's my other hydrogen, and then here's the oxygen in the center. And you'll notice that they have done the electron arrangement for that. So 2 in the first, and then 8 in the second, and then 8, and then, well, now we know better that it's actually more complicated. The thing I wanted you to hopefully get from this one, though, was when you're looking at this and they're doing their bonding, yes, you have, again, that shared electron for that bond. And now this is stable as an outer ring. But the thing that I wanted to kind of remind you guys of is that when we're talking about Lewis structures, we are only talking about the valence shell. We are not concerned about any of the inner electrons. So the bonding only occurs with those outer shells there. So that's why this center shell here is not involved at all. And no matter how much I kind of shove it in there, move it around, it's not going to change it. Same with the carbon dioxide. So if I pull these guys apart, these one here has 6, 6, 4. So in order for that center one to have 8, that's why we're starting to see those double bonds. But again, you can notice that it's not actually doing anything to the inner shells. And then same thing with ammonia. So that's what I wanted to get away from the first kind of point. I think last year I taught it that there were 2 ways to do this, and now I'm just teaching the one way because I think it's the better way and the more useful way for level 3. Okay. So just to kind of recap what we talked about last year. Can you see that all right?
Yeah.
Okay. I don't want to get you in the frame. You don't want to be in a. So, oh, I don't black. I want my beautiful colors. Okay. So first, let's think about ammonia. Paper this way. So you had, say, for example, NH3 is what we were just looking at. What you need to do is you need to figure out how many valence electrons you have for each element and also how many atoms you have of each element so you know how many electrons you're working with total. So the way we're going to do that is by looking at the periodic table, which is here. So we're looking to see what group they're in because that tells us the valence shell. So these are the ones that will follow that pattern. We skip the stuff in the center because, as you know, it's a lot more complicated. It's going back up and down kind of thing. So when I look at for ammonia here, it's over here, and this is group 15. If I count it, it's going to be 15 over there. 15 means it has 5 valence electrons. So 1 valence, 2, then we're up to 13. So that's 3 valence, 4, 5, 6, 7, 8. Okay. So for the nitrogen, what I'm looking at is we have 1 atom, and we also want to look at its valence shell. or multiplying those two things together. So I only have one atom of the nitrogen. Its valence shell only has 5 electrons, so I have 5 electrons that are being contributed from the nitrogen. Next one I have is the hydrogen. I have 3 of them. And then on the periodic table, when I look, I see that hydrogen's over here in group 1, so it only has 1 valence electron again. So 1 times 3 is 3. And then I add these together, so I have 8 electrons to work with in order to make my Lewis diagram. The next thing I need to think about is which of these 2 atoms are going to be the center atom, and the center atom is the one that can do the most bonding, because we want to be able to build our molecule up.
Okay.
So what I'm looking at, let me go back to here. So you see how with the nitrogen, it has 1, 2, 3, 4, 5. So in order to get to 8, it needs 3 more. So it actually has 3 bonding locations. Carbon has only 4 valence electrons, so it has 4 bonding sites, which is why carbon is such a good builder, like a Lego piece, basically. Oxygen, if you look at it, 6, so only 2 spots to do those covalent bonding. So that's why when we're looking at these things, we have to think, okay, which one has the most availability to be building? And in this case, it's going to be the nitrogen. So I put the nitrogen down. The other thing I must assume is that in order for my atoms to be attached as a molecule, they need to have to be at least 1 bond. So hydrogen, 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 because there's 3. And then the 2 dots represent a covalent bond, because that's how many electrons are in a covalent bond. I need to do some accounting and keep track of all these electrons. I know there's 2, 4, 6 that have been used. So if I subtract away 6, I have 2 left over. The next rule is I have to go outside going in when it comes to filling it. If things are already stable, then I can move on into the next bit. So this is stable, and that's stable because hydrogen only needs 2. So now that means I can go to the center atom and put these 2 extra electrons. That's what I'm doing here. Like that. And that's my Lewis structure for that one. Something that you can do is you can do lines to represent the electrons that are in bonds and the electrons that are not in bonds, which is really useful because then you can actually distinguish between lone and bonded pair. And that's going to be important when we're talking about shape and when we're talking about polarity and things like that. So it is useful to do this, but you'll be marked correct for either or of these options. Next one I'll do is carbon dioxide, just to show you how these double bonds arise. And then we'll start looking into the what's going to be new for this year. Let's see that too. All right, so I'm going to keep my head out just to make sure they're still fine. All right, so we're doing the same process again. So carbon, I have 1 of it. And then when I look at the periodic table, I see that carbon's in group it's in group 14, so that's going to be 1. I actually have these memorized. I'm just showing you.
Okay.
All right, next one is oxygen. There's 2 of them, and it's in group 16, so that's 6. So 6 times 2 is 12. And then I add those 2 together. That makes 16. Making sure I have my math. All right. So again, when I'm thinking about this, I need to think about who's going to go in the center. So should it be carbon or oxygen?
Oxygen?
How many bonds can oxygen do? If it has 6 electrons, how many spaces does it have?
3.
Only 2, because we're getting to 8.
Oh, okay.
Yeah? What about carbon?
That's 4.
So carbon then should be in the center.
Okay.
Do the most bonds. So carbon, oxygen, oxygen. We assume that there must be at least 1 bond to attach everyone together. And so now I've used up 4. So now I'm down to 12.
Okay.
All right. Next step is I go outside in. So I have 12 to work with. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So I've actually used up all my 12.
Okay.
All right. Now I'm going to double check just to make sure everyone's stable. So that way, yeah, it's all for stability, right? So oxygen here, 2, 4, 6, 8. That one's stable. Carbon, 2, 4. That's not stable. And then this oxygen, 2, 4, 6, 8. So that one's stable. So these 2 are stable. This one is not. So at that point, because we have that issue, what we're going to do now is we're going to remove some of these shared electrons that are, sorry, some of these lone pairs of electrons to becoming shared electrons in the center. So it doesn't really matter which ones you take because they're all correct. I'm just taking those out ones because I like to have a symmetry. But if you took the top ones, it's fine. So that's what I'm looking at here for my molecule. So when I go to draw it, I would have O, C, double bond O, dot, 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 dot. That's my answer. So that's how I know then when double bonds are occurring. Something to keep in mind is that there are a few exceptions to the rules when it comes to what they need for stability. So basically, the rule that we're looking for is 8. The ones that are exceptions to that is hydrogen. Hydrogen's happy with 2. There's also beryllium and boron. And they go in order of the periodic table, so that's why I was checking that. Beryllium's stable with 4 electrons, and boron is stable with 6. So you don't have to fill the shell to 8 for these guys.
Oh,
That's basically what that's talking about. Unlikely going to ask that this year, but potentially they could because, it happens. But the focus of this year should be on the extended octet. So now that we're talking about things that are large, and we talked about our little subshells, let me go back to the notes when we did that. It's basically lesson 1. Okay. So looking at this, wait, it's in your notes too. Hey. Oh no, it's the previous notes. It's fine. It's on the board. So the thing to keep in mind with this extended octet, everything we were doing last year was really simple stuff. Once you get to silicon on the periodic table, something to keep in mind is that there's this valent D shell. So what can happen now is that if I have more than 8, I can start putting the extra electrons into this D shell here. And that's what the SciPad is trying to explain to you when it's looking at the electron configuration. It's just saying, oh, there's an empty D shell here. We can start putting things in here if we need to. You don't actually have to do any of that for the assessment. It's just trying to explain to you the theory of what's going on. So when we talk about extended octet, we're just talking about larger molecules. And the reason why these larger molecules can form is because it can now occupy that 3D subshell. So it's just like an empty 3D shell or an empty, 4D, just like an empty D shell.
okay.
So I'll write that down. Go back. Go back. Okay. So this year we're going to be learning about the extended octet. Extended by filling vacant D shells. That's basically what's happening when we're doing that.
Okay.
Let me pull up some examples to do as practice just so you can kind of see it. And then it's pretty straightforward from there. Just find you some. The exam question just to kind of work your way. We should have you doing some Lewis structures. There we go. Cool. So we have Se4F. I just want to find an ion one as well. Kind of show you what it looks like too. Trying to find one that I will like to see. Or that there should be answers at the back. I just want to see an answer so that way I know I'm doing a good molecule for you. That's all. Cool. Yeah, we'll do this. SF4 as our example first. Okay. Back to to that one. Okay, so we're looking at SF4. So first thing we're looking at is the sulfur. So sulfur on the periodic table is in group 16, and we only have one of them. So that gives me 16 electrons. Fluorine then is in group 17. We have 4 of them, so times 7. Oh, now I have to do my math. 28? Did I do the math right? I think that's right. Might grab my calculator because I don't know if I can do this mental math. All right, and then 6, 8, so that would be 4, carry the 1, 34 electrons. All right, I'm just looking at you to make sure I'm just grab a calculator because I don't trust myself. Okay, I'm pretty sure that's right.
Yeah, it is.
Okay, cool. All right, so when we're thinking about this guy here, again, we're starting to think about, okay, which one can do the most bonds and thus should be at the center. And also, like, symmetry-wise, what makes sense to be in the center? So this case, sulfur makes sense to be in the center because we have all these 4 fluorines. So I'm, again, assuming sulfur's in the center. We have 4 fluorines, and I have to assume that it's attached with a single bond. Otherwise, you know, it's just floating out of nowhere. Right now, I've used 2, 4, 6, 8. So I have 34 minus 8, which is 26.
Yes.
Oh my gosh, I feel so good. Okay. So now it's 26 left. Again, we go outside going in to use up our electrons. So 26 are left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I have 24 that I've used and I have 2 left over. Now what happens is the extra 2 electrons go onto my center atom. And it's the extended octet. Because sulfur, like I said, can occupy that vacant D shell.
Okay.
So that's what that looks like for these Lewis structures. If you're given, so that's that. That's basically the same process. If you are dealing with anything that is an ion, I don't know if you want an example of it or not, or if you're just happy to see it. So this, for example, is an ion. The difference between a molecule and an ion is that you have to factor in the extra electron or the loss of electrons. So since in this case here, we have gain an electron, I then have to add that to my total that I'm working with. Do you want me to work through it just to show you?
Please.
Okay. So let's say I have ClF4 minus. So again, same math. Chlorine, you have 1, it's 7, so that's 7. Fluorine is 4, you have 7, that's 28. And then I also have that 1 extra electron here, so I'm adding that as well. So I believe that's 36. Done my math correctly. Yes, it is. I'm confident about that one. All right. Are you okay with that?
Yeah.
Okay. Now I do the exact same thing. So again, because of the repetitiveness, chlorine's going to be in the center. I assume everyone has to have a single bond. So 1, 2, 3, 4. That has used up 2, 4, 6, 8 electrons. So now I'm down to 28, I want to say. Yes. And then going from the outside in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So I've used up 24. So now I'm down to 4 more. So 1, 2, 3, 4. All right. The other thing that's different with the ion is you need to put it in square brackets. You can't see my dots anymore. And put the charge on the outside. That's the only additional step.
Okay.
And that's it. All right, let me just check that answer's right. Yes, it is. Okay, cool. All right, so that's that. So now what you can do is those SciPad pages, just so you can feel confident. I don't need you to do all of them because it is quite repetitive. If you want to do the level 2 recap, you can. It is very unlikely level 2 molecule though. It's just good if you want to practice double bonds. But again, a lot of these larger structures don't typically have the double bonds. They just kind of stick some extras. You might find a couple with double bonds just to kind of make up the space that's needed. But I don't think I have seen that happen a lot. I don't think so, yeah. So it's easier in that sense. Yeah, I don't see any double bonds in here. So it's your call what you want to do. So yeah, get that done as your next step. And then once that is done, you can move on to the shapes lesson. Again, it's going to start off with using a simulation just to kind of refresh from last year. And then, like I said, call me over once you're ready and I can give you the notes on that one.
Okay.
Okay?